Let's examine quantum mechanics. This is revision, so we'll go fairly fast. Let's just cover why it exists. Why do we go beyond our lovely classical physics? In classical physics, we used to have light. Here's a laser emitting a laser beam. And if we put our laser beam through a couple of slits, we get a beautiful interference pattern. And we also have stuff. We have matter. So we might have, I don't know, an electron gun. Electron gun you can get out of a very old television. Boom, boom, boom. And that spits out a pile of electrons, and you put that through a couple of slits, and you probably expect to see just them bouncing through. However, if we actually do these experiments physically, and we turn down this laser, we get clicks, which means that these things come in quanta, where the name quantum comes from. These quanta of light are called photons, and that's what Einstein was given the Nobel Prize for. He postulated the existence of photons in describing the photoelectric effect. In fact, electrons, if we do put them through two slits, something rather interesting happens. If we throw them in on a detector, we actually get, well, we get our dots appearing, but over time, they actually form beautiful bands exactly as though they were making the interference pattern that we'd have expected them to do if they were waves. In fact, interference is something that only waves can do. You can't have particles deciding to just stop existing when they meet each other and they have different phases. That's a property that waves have. We have things that come in and out of phase. And indeed, the fact that electrons, which also obviously had quanta, were really waves, and that photons, which were clearly waves, also had quanta, suggests that actually we needed a theory that sort of crossed between the two. In fact, quantum mechanics explains why we have things like atoms. If we had old-fashioned classical atoms with electrons in orbits going around them, electrons, charged particles accelerating around like that would emit lots of energy, and atoms wouldn't even exist. And so, of course, these quanta that are so important in describing these things also describe why atoms exist at all. And so we have all sorts of phenomena that we really need quantum mechanics to explain. So what's the critical principle in quantum mechanics that we can't do without? It's basically that in every case, the state of an electron, the state of a photon, an atom, a nucleus, or anything, anytime you have a valid state, then the superposition of that with another valid state is also a valid state. So something that waves can do that particles can't, but everything appears to be able to do, is be in a superposition. Now, what kind of mathematical theory do we need to describe things that in general are in a superposition? Whatever the state might be, if two elements of that, so if I have one element and another element, and they're both valid states, if some linear combination of those two is always a valid state, in some sense, then what I'm living in is a vector space. And so our first key postulate of quantum mechanics is that everything is described by an element of a Hilbert space. And a Hilbert space is simply a complete vector space with an inner product. Now, if you're having a mental blank about what a vector space is, if you type vector space into Google and hit return, the top link will tell you all about it. Basically, a vector space is a bunch of elements. This addition here is associative and commutative. It has a zero, i.e. an identity, and an inverse. So in other words, if you've got a psi, then there exists a minus psi. It's also got a scalar, so you can multiply any vector by a scalar. Our scalars are always elements of complex space, so our scalars are always a complex number, and we can multiply by any scalar, and these are distributive and have an identity as well. So vector spaces are simple, example vector spaces. There's the space of position vectors, there's the space of momentum vectors, all the kinds of things we've been talking about, all those rules exist. So everything is linear, in short. Vector spaces are mathematically simple objects. Okay, so let's have a look at some examples. So I've said everything is described by an element of a Hilbert space. Different things, of course, have different dimensions. They have different numbers of degrees of freedom, and so we need to have some different kinds of examples here. If we would look at a photon, now if we have a photon in a single spatial mode, it still has two possibilities. It could be a horizontally polarized photon or a vertically polarized photon. And it turns out you could also have it polarized at 45 degrees, but it turns out those two are enough to be a complete basis. What's a complete basis? A complete basis is any list of vectors that you can write an arbitrary vector, so an arbitrary state of polarization of a photon can be written as a linear superposition of these basis vectors. So in other words, a completely general state can be written as some number times the horizontal polarization plus some other number times the vertical polarization. Other examples, we might have an electron. Now, an electron has lots of degrees of freedom. It could be here, 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 and so all of those different positions are independent states it could be in, and indeed, together they make up the basis. So a completely general state of, say, and in fact it's also got spin degrees of freedom, which we're ignoring, so a completely general state of a spin-up electron would actually look like a superposition of these. Now what's the superposition of these? It'd be a sum of them. In fact, because this is a continuous index, it's actually going to be an integral of them. So there is a completely general state of an electron. And again, it's just a superposition of states. A bound electron here might be more naturally written in terms of all the possible energy states it could have, which we might describe as, I don't know, EJ, the energy states. And indeed, if this is a basis for electron, then this is just a different basis for the same object. Okay? But in this case, a general state would look like a sum over J of all of those states. So we have finite, infinite but discrete, and continuous. These are all vector spaces. These are all Hilbert spaces, and they describe different physical things. Actually, those two describe the same physical thing. But we can have quite different looking Hilbert spaces depending on the different thing that we're describing. But they all have the same kind of mathematical structure, which is pleasant.